This lesson is about kinematics. It's one of the tools we'll be using a lot in this class. It's the analysis or study of motion. Before we get into that, I just want to go over two types of quantities we have in physics. There's scalars and vectors. And pretty much they both have numbers associated with them. For example, your mass, or the mass of an object, might be 5 kilograms. Um, so something like mass has a number associated with it, 5 kilograms. But it does not have a direction that is associated with that quantity. Um, so mass is a scalar, and vectors are quantities that not only have a number or a magnitude associated with it, but a direction. That's important to know. So, for example, if you look at your phone and it's been tracking your distance all day, that's just a number. It'll say, oh, you've walked, let's say, 2 miles today in total. There's no direction associated with it. It's just like a total distance that you've gone. Displacement, on the other hand, just draw like a little number line here. 1, 2, 3, 4. If you start at position 0 and you walk over to 4, and then eventually you walk back to, let's say, so yeah, you start here, you walk over to 4, and you come back to 2. Okay, let's go back to distance. The distance that you walked was 4 units this way plus 2 units that way. So you walked a total of 6. Your distance was 6, let's say, meters is this unit. But your displacement is how far you moved from where you started and in what direction. So you started here, you ended here. So your displacement is 2 meters to the right. Okay, so again, distance is a scalar, displacement is a vector. Okay. Some other ones, speed. If you're driving in your car and you look at your speedometer, it just tells you how fast you're going. It's a number with units. There's a magnitude to it, it's like how much. But velocity is your speed plus the direction that you're going. So if you're driving 30 miles per hour east, okay, would be like a velocity. Okay, and two more scalars would be, we talked about mass. Time is a scalar, it's just a number with units. And some vectors, which these are not related necessarily. Mass and acceleration are two different things. But acceleration is a rate of change of velocity, but there's also direction associated with it. When you push things, when you put a force on objects, the direction does matter. Those are vector quantities. While we're speaking about direction, it's important to note that when we do mathematics with this, we have to indicate our direction. Right now, we're going to use positive and negative to indicate direction. And this is only for this lesson, the next couple of lessons. If we're saying positive, what that means is I'm moving in the positive x direction. And so we can say that this means, for example, forward or to the right. And of course, if we are moving in the negative direction, negative x direction, we can say that's moving backward, or we can say that's left. And we'll do some examples here in just a moment um, to really see how that works. Okay. In past lessons, we've looked at position time data, typically for objects that are going at constant velocity, constant speed. But if you look at this position time data, just look at those positions versus time. How would you describe the motion of this object? You can take a moment, pause the video, think about it. And if we do a quick calculation, and what I'm talking about is change in position versus a change in time, my change right here from 4 to 16 is 12 meters of change. And my change in time here is 2 seconds. So 12 over 2 would be 6. So the speed of the object is 6 meters per second in this interval right here. Well, let's keep going. What's the change here? So 52, to do this in my head, looks like 36 meters of change. Let's see, is that right? It's right to me. Difference here is again 2. So change in 36 over 2 looks like 18 meters per second. So this object is increasing in speed, increasing in velocity. And we can keep doing this. We can keep calculating. And sure enough, the speed of the object will be increasing. We would describe this as acceleration. The object is accelerating. Okay? Whenever speed changes for an object, velocity, excuse me, whenever velocity changes, that's an acceleration. And here are those speeds. So we have 6, 18. I didn't do the math here, but it would have been 30, 42, and 54. Now, the same way we got velocity with position time data, we can sort of get an average acceleration using a change in velocity over time. This would be time. Okay. 18 minus 6 is 12. 3 minus 1 would be 2. So again, this would be 6. Now it's 6 meters per second of change every second, but we don't write it like that. We write it, you can also just say, we write it as 6 meters per second squared. 30 minus 18 looks like 12 once again. 5 minus 3 is 2. So 12 over 2 is again 6. So this object has a constant acceleration of 6 meters per second squared. And so let's go to the next page. So we can define velocity as a rate of change in position, and we would define acceleration as a rate of change of velocity, and that's with respect to time. Okay. It's important to know those. Velocity is a rate of change of position. Acceleration is a rate of change of velocity. Okay, now let's get on to kinematics. We'll be using 6 quantities. The position of some object at the start of time, time 0. So this first one, we pronounce it x naught. Or you can say x0. Or you can, we basically say those. So x naught is the position at time 0. X by itself is the position at some later time. V naught, that's how we say that, is the velocity at time 0, or the initial velocity, sometimes we'll say. V is the velocity at some later time. A is the variable for acceleration, and T for time. I've put the units over here. This is meters. This is also meters. These are both meters per second. Let's write that better. We say meters per second, not m over s or anything silly like that. This is meters per second squared, and this is seconds. All right. These are the three equations we'll be using for some time. I just call them equation 1, 2, and 3, just so we can easily refer to them. And just shortly we will use them. These equations, it's important to note that they are only valid if the acceleration of the object is constant and if the motion of the object is one-dimensional. That means along an axis. So like if you have your x-axis like this, you can even have a tilted axis. Like for example, a ball that's rolling on a slope would still be one-dimensional. And even for an object that's falling through the air, which will happen later, is one-dimensional. It's just going in a straight line. If the object is not going in a straight line, then these equations do not apply. And if the acceleration is not constant, then these equations do not apply. Let's go ahead and jump into some problems. Example 1. And by the way, as I'm showing these problems, it's important to note the process in which I do them. This is the process that you should follow for each of these types of questions. It says, Otis the cat initially moves to the right at 2 meters per second. He then accelerates at 1.2 meters per second squared to the right for 3 seconds. Okay. First thing we should do is, I'm going to write this really small because I have very little space here. Let's make a list of the variables. And feel free to pause at any time if I'm going too fast. So Otis the cat initially moves to the right at 2 meters per second. So again, this is where you really have to maybe go back to your notes and read these. So velocity at time 0 is where that number would go. So it's got a speed and a direction, so that's velocity, and it's initially moving it, so that's at the start of the problem. We're going to say 2 meters per second. The number should be positive. That's to go with the direction right. Okay. So he then accelerates. Now, if you look at those units, there's only one place this number can go. This is an acceleration, 1.2 meters per second squared. And the cat does so for 3 seconds. Looks like at first that those are all the numbers that they give us. Even if you read the questions, it seems to be the only numbers they give us. But oftentimes when they don't tell us what the initial position is, so if you just imagine your cat here. Oh, that's a terrible picture. Let's see here. And your cat is initially moving to the right. Let's just make the starting point of the cat 0. And wherever the cat goes by the end of the problem after 3 seconds will be how far the cat has gone. Okay? So we're going to do that often. If they don't say where x naught is, where it's starting from, just make that 0. All right. So whenever you solve these problems, make sure you have your list. And when you do your work, show me which problem you're solving, A or B. And let's do A first. So it says, how far did Otis move in this time? That would be x. We need an equation for x. So we'll look for an equation with x, but we need to note that we don't have velocity. So our equation should not have two unknowns. You don't want to have an equation that has x and v. Let's make sure it has x, but it's missing v. And these you want to write on your notes and keep them handy. Okay, so this has x and this has x, but this one has v, and so we don't want it. This one has v naught, which is fine. We have v naught, so that's okay. So we'll use this one. By the way, very important to note here, as it will become relevant eventually, pluses and t's. If you make your t's like this and you make your pluses like this, that can get very confusing. So I write my t's with a little curve. I write my pluses, the normal way. But if you write them like this, you tend not to confuse them. So for example, here, if I wrote this, trust me that this gets confusing. So write it like that. All right, let's solve this. To get full credit on these problems for homeworks, quizzes, tests, make sure you are writing me the whole equation the same way it was written in the notes, without any numbers inserted into the equation. Just straight off of the board, if you're writing this from the board during a quiz or something. That would get you a point. And let's go. So we don't know x. So when you don't know it, just leave it. X naught is 0. And if this was multiplied by something, I would maybe want to write it in there. It just depends. But in this case, if this is 0 and you're going to be adding it with this other stuff here, we don't really need to put it. We're just going to cross it out, say it's 0. And I'm not even going to write it here because there's no need. V naught is 2, so I'll just keep going. Whenever you substitute something, you should put it in parentheses. 3 plus 1/2. And A is 1.2 and 3 squared. Cool, so this is 6. Now I wouldn't normally do it this way. I would just type this all in a calculator. But my calculator is not near me right now. So 3 squared is 9, half of 9, 4.5 times 1.2. Well, I have a calculator on my phone. Looks like 5.4. So this is all 11.4 meters. That's how far Otis moved. You can write this number here once you have it, but I am grading it over here on quizzes and tests. I'll show you how I grade in just a minute. So make sure it stays here, box it for me. Cool, last question. We need to solve for V. When you have all the numbers except the one you're looking for, you can use any equation you want. And so the easiest equation for V is the first one. V naught is 2. So it looks like 3.6 plus 2, 5.6 meters per second. Okay. Now, on a quiz, it changes, but I would generally give you a point for writing your equation without numbers. Most of the time, a point for substituting the correct values in the right places here. Like in other words, a correct substitution, correct answer. Any equation that will get you V. And by the way, this one also works. This is your third equation. It's just longer. We'll get to use that here in just a moment. So you could have used either one of those. Typically, I'll give you a correct point for a correct answer and a point for units. So both of your answers have units in it. So this might be worth 6 points, typically. Let's keep going. Let's make a list. A bicyclist, initially at rest. This is an important word. accelerates to the right to a final velocity of 10.2 meters per second over a distance of 17.34 meters. So, they do not give us the initial position. Whoops. So, we're going to put 0 for that x naught. Sorry, I don't like how these looked. Now, we can go in order or out of order. Let's start with the word rest. It's a very special word. That means it's motionless. So a bicyclist is initially motionless, so no speed, no velocity. So its initial velocity would be 0. It accelerates to the right to a final velocity of 10.2 meters per second. By the way, whenever you put 0 for these, you don't need to put units. You can just put 0. And I think, oh, we have one more. A distance of 17.34 meters. Cool. Question A, what is the acceleration? Now, we need an equation for acceleration, but they all have acceleration. You have it here, here, and here. So, we just want to make sure that it's excluding the t. We don't want an equation with t, and the first two have t right here as well. So it's going to be equation 3. But we are solving for a. So we're solving in the middle of the equation, for a in the middle of the equation here. Let's substitute v. Whenever you substitute, put it in parentheses. V naught is 0, and 0 squared is 0, and 0 plus 2a x minus x naught, we can just get rid of that. This is 2 times a, and we'll substitute 17.34. Okay, x naught was 0. Whenever you subtract 0 from things, you just keep that number. Let's square the 10.2. 104.04. Let's multiply 2 and 17.34. We get 34.68 times a. And so we just divide. And we should get 3. Now, acceleration is a vector, so I think I'll write it like this. It's positive, so that acceleration is to the right. Write it like that. Oh, and I realized, if I go back to this one here, velocity is a vector. And you'll have to excuse me, I'm kind of just doing this on the fly. I didn't think about the lesson very much before I sat down to record. So let's just erase all this. 5.6 meters per second to the right. We want to be comfortable with direction with these vectors. All right, let's go back to over here. Okay, we have our acceleration. We can put that here. And we just need to find t. The easiest equation for t, when you have everything else, is the first equation. If you can use that first equation, take advantage of that. B naught is 0. A is 3. By the way, you don't write direction or units while you're working the problem. You write it just at the end. So we'll take 10.2 divided by 3. and the time was 3.4 seconds. Cool. The scoring here would be roughly the same as the last one. Okay, let's keep going. A ball rolls uphill at 4 meters per second, slowing down at 1.5 meters per second squared. What is the velocity of the ball after 5 seconds? And how far up the hill is the ball at this time? Just going to draw a picture of this. So the ball is headed up here, uphill at a velocity of 4 meters per second, up, and it's slowing down. So here's something very important. This is clearly an acceleration, meters per second squared, and it says that the ball must be slowing down. So here's something to note about acceleration and velocities. Let's take out the 4 for a second. Let's just say this is the velocity. Let's keep it simple. This is the velocity. If I write in that the acceleration is positive, in other words, going with the velocity, this would imply that the ball is going to start speeding up and get faster and faster and faster and faster, which can't be true in this case. We're just rolling a ball uphill. You guys have ever played skee ball? It's kind of like that. It rolls up, and let's say it didn't make it in the hole, it'll just come back down. So the acceleration must be in this direction, because then the ball would be slowing down, make it up to a high place, and then it would roll back down like that. Okay, so let's put a side note over here. When V and A are in the same direction, the object is speeding up. We'll say speeding up. And vice versa. So when V and A are in opposite directions, the object is slowing down. Sorry for the handwriting. I hope you can just hear me and you can just write from how I'm speaking. So the acceleration of back with example 3 must be going the opposite direction. So even though they tell us it's 1.5, it really should be negative 1.5. Let's make our list. They don't tell us the starting position, that's 0, which is right here. It is rolling uphill at 4 meters per second, and it is slowing down at 1.5 meters per second squared of acceleration. Okay, question A, what is the velocity of the ball after 5 seconds? The 5 seconds would go here. And then B, so we're looking for V, and then we're looking for X. Okay, sorry, don't put those question marks in there. So for part A, we want to solve for V, and the equation must be missing X. Well, that's equation 1. So V is equal to V naught plus negative 1.5 times 5 seconds. Okay. 5 times negative 1.5, 4 plus negative 7.5. And of course we get negative 3.5 meters per second, which we should not leave that way. We should write it as positive, and we'll say that is moving. So it says uphill is positive, so this would be downhill. Or you can say backwards, the negative means the opposite direction on the axis. So what that implies is the ball has gone up, it's made it to its highest point, and it has started to roll back down. After 5 seconds, it is moving, negative 3.5, which will be somewhere right here, let's say. Okay, I need the space. All right, part B, the simple one now. How far uphill is the ball at this time? So we can use any equation. Oh, but I think I like this one. Do I like that one? I think so. At 0, whoops. Velocity is 4. T is 5. Oh, we can just type this in the calculator. So its position is 1.25 meters at that point. So this would be x, this would be x naught. And I forgot to write this here. Typically, we'll tell you how to label your directions, right or left, forward or backward. This is uphill, so the opposite is downhill. Later on we'll be going up, going down, that sort of thing. Okay, last one. This one is an example without numbers. So let's just start our list here. Okay, a car is initially at rest. So V naught is 0. Starts moving forward with an acceleration A. So they don't give us what A is, but we're going to put A because that represents whatever that acceleration is, to a final speed V. And so we'll put V for V. In terms of A and V and other fundamental constants, determine the following. Derive an equation for the time t, and derive an equation for the distance d. So let's put 0 here, as we normally do. And the distance it goes, well, that would be normally x. Now, we can't have d in our equations. We want a and v in our expression. So let me just show you how we do that. Let's do part A. Okay. The simplest equation for t, for time, is this one. V naught is 0. And we want an equation for t in terms of a and v. So we want to just isolate t because we already have a and v left in the equation. So let's just isolate t. That would just be v over a. And that's it. When we're done here, we should always check, is our answer in terms of a and v? And it is in terms of a and v. So we're good. Yeah, it doesn't say have your answer in terms of t, but we're saying t is equal to v over a, so it's okay to say t equals v over a. And then finally, derive an equation for the distance d. Um, we will often use this equation for whenever we're solving for x. Okay, so write out the full equation. X is d, so we are substituting. Okay, x naught was 0, v naught is 0, and by the way, 0 times t is also 0, and I'm just going to cross it out because 0 plus, we don't need to put all that. This is 1/2. A is a, and okay, we have t squared, but I don't want to leave t as t because we can't. We have to have it in terms of a and v, but we know t in terms of v and a. So I'm going to substitute for t, that's v over a, but don't forget the squared goes there. Now, later on we won't do this, but remember that v over a squared is just v times v over a times a, right? Or v squared over a squared. But when we do it this way, it's very easy to see. We can cross those out. And so, let's see, we're going to have a v squared times 1, and on the bottom is going to be 2 times a. Is our answer in terms of v and a and constants? Yes, it is. And that's it. Please come to tutorials if you still have questions.